For the first problem with elastic collisions, we have the air track situation where both carts are initially moving toward each other. They have two different masses. They're going to collide elastically, and we want to know what happens to them after that collision, what their final velocities are. So on these problems, always a good idea to separate your given information into what's happening for each object. So for the red, I've got a mass of the red one of 1.0 kilograms, and initial velocity for the red one of 1.0 meters per second to the right, and an unknown final velocity. For yellow, got a mass of the yellow one is 0.50 kilograms. Initial velocity for the yellow is 1.0 meters per second left. Notice that those are in opposite directions, so we need one of them to be positive and one to be negative here. And an unknown final velocity. Since we know that they collide elastically, we can do both conservation of momentum and conservation of energy in this problem. So we'll start with conservation of momentum. Total initial momentum equals the total final momentum. Or if we expand that, the mass of the red cart times the velocity of the red cart initially, plus the mass of the yellow cart times the velocity of the yellow cart initially, is going to be equal to the mass of the red cart times the velocity of the red cart finally, plus the mass of the yellow cart times the velocity of the yellow cart finally. And now we can substitute values for those. We've got 1.0 kilograms, and I'll make this a positive 1.0 meters per second, plus 0.50 kilograms, and this one will be a negative 1.0 meters per second. Set that equal to 1.0 kilograms times the velocity of the red one final, plus 0.50 kilograms times the velocity of the yellow final. Alright, over here when I calculate this, I've got 1 times 1 is just a positive 1. 0.5 times negative 1 is a negative 0.5, so on the left side I end up with 1 plus a negative 0.5, or just a positive 0.5 kilogram meters per second. And we'll set that equal to 1.0 kilograms times velocity of the red final, plus 0.50 kilograms times the velocity of the yellow final. And I'm going to go ahead and divide everything by a 0.5, just so I'm working with whole numbers here. That'll be useful when I go to the graphing stage too, because I'm going to have a coefficient of 1 on one of these, and I'll have it on the yellow one instead of the red one. You could do it without this step. I just prefer to work with whole numbers if I can. So I'll divide everything by 0.50 kilograms, and that gives me 1 meter per second. It's going to be equal to 2, and the kilograms cancel here for units. 2 VRF plus just a 1 VYF. Okay, so that's one of our equations. We'll come back to that one once we've written the other equation using conservation of kinetic energy. So the second equation, we say the total kinetic energy initial equals the total kinetic energy final, or 1/2 m red initial squared plus 1/2 m yellow velocity yellow initial squared is equal to 1/2 m red velocity red final squared plus 1/2 m yellow velocity yellow final squared. Again, since the 1/2 appears in every term, we can divide everything by 1/2 and get those to cancel out, so we don't have to deal with those. Now we can plug in what we know. We get 1.0 kilograms times 1 meter per second, and that gets squared, plus 0.50 kilograms times a negative 1 meter per second, and that gets squared, so we'll lose our negative sign there, plus 1.0 kilograms times the velocity of the red final squared plus 0.50 kilograms times velocity of the yellow final squared. So over here I've got 1 times 1 squared is just going to be 1. 0.5 times a negative 1 squared. Negative 1 squared is a positive 1. So positive 1 times 0.5 plus 1, that's going to give us 1.5. And the units here are going to be kilogram meters squared per second squared. That's the same as joules. I'm going to do some unit canceling in just a minute anyway, so I'll write it out as kilogram meters squared per second squared. And then that's equal to, I made a mistake in how I wrote that. That should be an equal sign, not a plus sign. Equal to 1.0 kilograms times V red final squared plus 0.50 kilograms times V yellow final squared. And again, I like working with whole numbers, so I'll just divide everything here by 0.50 kilograms, and I'll end up with 1.5 over 0.5 is 3 meters squared per second squared is equal to 1.0 divided by 0.5 is going to be 2 V red final squared plus 1, so I don't really need to write the 1, I guess, 1 times V yellow final squared. Okay, so now I have my two equations. I'm going to graph these and see where they intersect. So to do that, I'm going to go ahead and rewrite these with x's and y's instead of VRF and VIF. So let's say that x equals the final velocity of the red one, and y is going to be equal to the final velocity of the yellow one. And so that gives us equations of 1 equals 2x plus y, and 3 is equal to 2x squared plus y squared. To graph these, I'm going to have to get them in the form y equals something. So this one becomes y equals 1 minus 2x. And this one becomes y equals, let's see, I'll subtract the 2x squared and then do the square root. And remember, you got to do plus or minus when you do a square root. So plus or minus square root of 3 minus 2x squared. Now, if you didn't divide by 0.5 here, that's fine. You'll just have 0.5, 1, and 2, or 0.5 there. And then over here, 0.5y, 1, and 2x. I guess you would need to divide by the 0.5 just to get the y equals all by itself. You might have chosen your y and x different from me. You might have said that y goes with the red one and x goes with the yellow one, and that's fine too. You would have just had these. At this point in the process, we need to solve this system of equations, and this one is, they're really kind of pains to do by substitution. So I'm going to solve this one by graphing. I'll show you how to do that on the calculator if you haven't done that before. So we're trying to solve this system of equation, these two equations. Where do those cross paths? So first step on this is to enter each of those equations into the calculator. So we had 1 minus 2x was one of the equations, and then the square root of 3 minus 2x squared was the other. But we really need to do plus or minus for that one, and you can't do that in just one line for the graphing calculator. So we'll do another one that's negative square root of 3 minus 2x squared. Okay, and then I'm going to graph this, but I want to make sure that I'm going to get kind of a generally correct size on my graph. So if you go to the zoom menu and then down to the last option, zoom fit, that'll automatically select a window that the calculator thinks is appropriate for this graph. It may take just a minute to decide what it thinks that is. And so now we see that there are 2 points where our graphs intersect. So the circle, or the oval here, that's That's one of our graphs. That's the square root of 3 minus 2x squared. And then we have the straight line. And they intersect here and here. And we can use the graphing calculator to figure out what those 2 points of intersection are. So we're going to go to second and then trace. So we're looking for the little calc option here. So calculate, we want the intersection between these 2 points. And the setup for this is it's going to ask you which graphs are you trying to find the intersection of first. So if you scroll left and right here, the cursor is just going to travel along whatever curve is being selected. If you scroll up or down, it's going to jump to one of the other curves, and it's not showing up on the graph here. Let's scroll over so you can see where that is. Somewhere in here. There we go. Okay. So we'll do that as our first curve. Second curve will be the straight line here. I'm going to find where they intersect. And then the guess, it wants you to place the cursor somewhere near where those 2 lines intersect. This is in case they intersect multiple times, so it calculates the one that you're interested in. So our first point of intersection here then, it looks like is 1 comma negative 1. And, oh, okay, got confused on this little symbol there. That's just a part of our axis. So a value of x is 1 and y is negative 1 for our first answer. And then we'll do the same thing again. So second, trace, and then back to intersect. And here we want to find the intersection between the straight line, and this time we want the top half of that curve. So I'll just make sure that it's up on that top half somewhere. And then for the guess, I'll scroll my cursor over. I'm kind of going to lose it up at the top there, but it looks like somewhere over here is where they intersect. And we get values of x is negative 1/3 or negative 0.33, and y is 1 2/3 or 1.67. So from our graph, using our calculator, we found 2 possible places where this works, where momentum and energy are both conserved. So we got values of x equals 1 and y equals negative 1, or x equals negative 0.33 and y equals 1.67. And I translated those back using x is the red final velocity and y is the yellow final velocity. And so our 2 possibilities here are either the red one is moving at 1.0 meters per second to the right, the yellow at 1.0 meters per second to the left, or the red is moving at 0.33 meters per second left, and the yellow is moving at, this is positive 1.7 meters per second, or 1.7 meters per second to the right. So now we have to decide which one is it. Well, if you look at these numbers, they ought to look familiar to you because that's the initial condition for this situation, that the red is moving to the right at 1.0, the yellow is moving to the left at 1.0. So after they collide, if they keep moving the way that they're moving, what that would mean is that one ball or one cart is passing through the other one. So that doesn't make sense. We have to have some kind of a change in velocity when they make contact. So the one that says velocity doesn't change, that one doesn't work for us. So this is the one that's going to work. So at the very end of this problem, we've got the final velocity for the red. Final velocity for the red is equal to 0.33 meters per second left. And the final velocity for the yellow is 1.7 meters per second right. For the second problem, we're looking at a Newton's cradle. And the Newton's cradle, that's just the little desk toy where you have the metal balls hanging and they crash into each other. We're going to simplify this by pulling 3 of the 5 balls out of the way, so we have just 2 that we're going to deal with, and we're going to pull one back while the other one is left to hang at rest. So we're going to pull one back and let it swing down and hit the stationary ball. Again, this is an elastic collision, and so it has to say that the balls collide elastically before we can use conservation of kinetic energy. So we can use that as well as conservation of momentum to calculate the velocity of each ball after the collision. Now this one, you've played around with these toys at some point before, so you should be able to make a pretty good prediction of what's going to happen when you leave one hanging, then you pull one back and release it and it crashes into the one that was hanging down. Think about what happens in that situation. So our results should match up with your intuition here. So I think it might be useful to sketch this one out just to establish some directions. I'm going to say one ball, we'll call it ball A, is moving to the right at 1.5 meters per second. There weren't any directions given, so I might as well call it to the right. And then ball B is just going to be at rest, and this is the initial state. So let's separate our given information, ball A and ball B. We've got the masses for each of these are equal, 0.20 kilograms, and for B, 0.20 kilograms. We've got the initial velocity for A is 1.5 meters per second, and I call that to the right. And initial velocity for B is 0. And then we're looking for the final velocity for each one. So again, we set up 2 equations, one with conservation of momentum and one with conservation of kinetic energy. So with momentum, the total initial momentum equals the total final momentum. So it's the same setup as the last problem we did, so I'll go ahead and skip the step of writing everything out with its variables. We'll have the mass of A, 0.20 kilograms, times the initial velocity of A, 1.5 meters per second, plus the mass of B, 0.20 kilograms, times the initial velocity of B, 0, equals the mass of A, 0.20 kilograms, times the final velocity of A, plus the mass of B, 0.20 kilograms, times the final velocity of B. And I notice that we have a 0.20 kilograms in every term, so we can simplify this by dividing everything by 0.2 kilograms. We end up with just 1.5 meters per second on the left side. And then on the right we have, just divided that, so it's just V final A plus V final B. Now we'll do the kinetic energy, conservation of kinetic energy. The total kinetic energy initial is equal to the total kinetic energy final. And so we'll do that. That's 1/2 ma v initial A squared plus 1/2 mb v initial B squared. Not plus but equals 1/2 ma v final A squared plus 1/2 mb v final B squared. Alright, and this one will simplify quite nicely as well. I see that I have a 1/2 in every term, so I divide everything by 1/2 and get rid of those. And then I've got these masses in each term as well. And the masses here are all equal, so I can divide by 0.2 kilograms again, and the masses will cancel out just like they did in the previous problem. So we get V initial A squared plus V initial B squared equals V final A squared plus V final B squared. Now the masses I only was able to cancel out because they're all equal to each other here. They're all 0.2 kilograms. So I'm saving myself a little work by making that cancellation. So plug in what I know. I've got 1.5 meters per second for the initial velocity of A. 0 squared is still 0. It's equal to v final A squared plus v final B squared. And so 1.5 squared is 2.25 meters squared per second squared. And that equals v final A squared plus v final B squared. Okay, so now I have two equations for my two unknown velocities that I'm trying to solve for. So let's do the same thing we did before. We'll graph these and we'll change everything to x's and y's. So I'm going to say let x equal v final A and y equal v final B. So my two equations then are 1.5 equals x plus y, which I rewrite as y equals 1.5 minus x, and 2.25 equals x squared plus y squared, which I rewrite as y equals plus or minus the square root of 2.25 minus x squared. Now we'll go to the calculator and graph both of those to see where they intersect. So once again we have a system of equations to solve, and this is another good one for solving by graphing. So let's set that up. So again, we're going to graph those two functions, and we had 1.5 minus x was the first function, and the second one was plus or minus, so we'll have to do this as two separate functions, plus or minus square root of 2.25 minus x squared. And then we'll do the negative value of that, square root of 2.25 minus x squared. And then zoom and fit. Right, and once again we have 2 points of intersection with this graph. So we'll go ahead and calculate that. So second, and then trace, and the intersection. And let's do this upper one first. So we need to pick the two graphs that are intersecting. So the line first, and then I'm on the curve, so that's good. And then my guess is going to be that it happens right around here. And we get a value of x equals negative 8 times 10 to the negative 17th. That's got to be an artifact of just how the calculator processes this. So times 10 to the negative 17th, that's tiny, 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 tiny. Let's just go ahead and call that 0. X is 0, y is 1.5. And then my other one, we'll do second, trace, intersect. And boy, it's kind of tough to tell where that intersects, whether it's the top curve or the bottom curve. I'm going to guess it's the bottom curve, and if not, it'll just tell me that they don't intersect. So first curve, and then my second one, bottom curve, and it looks like they're somewhere around here. No sign change, okay, so quit. Graph, and then we'll try it the other way. So intersection with the straight line, and let's do the top curve this time. I guess is somewhere over here. Okay, and so on this one we get, oh, that's the same one that we had a minute ago. Okay, so what that tells me is that there must not actually be an intersection point there, or at least not a real intersection point, maybe just an unreal one, an imaginary one. So we only have one possible answer here, and that is that x is 0 and y is 1.5. So let's put that back into the context of the problem and see if that makes sense. And so by graphing on this one, we find that x equals 0 and y equals 1.5, which means that the final velocity for ball A is 0, for ball B is 1.5 meters per second to the right. So if we look at this situation, initially A was coming toward B at 1.5, B was at rest. After this, A is going to be at rest and B is going to be moving at 1.5 meters per second, which should match with your intuition on this. Having seen this toy, you know that one ball, the ball that's moving, comes to a complete stop, and the other ball shoots out about as fast and about as far as the first one was released.